The secret of ASML has been that it's Dutch.
Hi, my name is Mark, and welcome to 4 Decades of ASML. In this third episode, I'm going to talk to Herman Boef and Marco Pieters, and they will talk about the time it took to bring EUV lithography from lab to fab, to a working EUV system. I'm also going to talk to Arie Dan Boef about his first experiments about an optical metrology system, which later became our YieldStar. And the external guest is Dan Hutcheson. He's an industry expert, and he will talk about the influence of smartphones and how it changed the semiconductor industry. Herman, Marco, welcome to this podcast, 40 Years ASML. This is the third episode. And in this episode, we're going to cover the period where EUV became mature, where it was industrialized and where it became economically viable to customers. And before we do that, Marco, can you give a quick introduction of who you are and what you do?
I said Marco Pieters, currently responsible for business line applications, and I joined ASML in 1999.
I joined in 97, currently the head of the Deep UV business line.
So let's go back to the Alpha demo tool, for instance, right? So that was sort of the pre-production EUV tool, you could say, that it showed the feasibility. But to bring that to where it would actually be economically viable to customers, where they would make money with it, right? So what was the key deliverable in that area?
Well, the main issue that we had was that we were lacking the source power. The source power, so the light source was not giving enough power. And that results in the fact that you cannot process enough wafers, which means that from an economics point of view, you cannot earn the system back.
Yeah.
Right? So you're lacking the productivity to be economically viable.
So for instance, initially it took hours to expose one wafer. And our customers always said, well, you need to be at least producing more than 100 or preferably 125 wafers per hour for this technology to be viable. And that was, I think, a big task to get that power there, that the expose time would actually go down significantly.
Because what was the power level then when you started?
So when we started, it was, I think, high single digits, watts.
Yeah.
And we needed for the 125 that Marco just mentioned, you needed 250 watts of source power.
Okay.
So we at least 2 orders of magnitude off.
Yeah. Okay. And did you have an idea where to begin? Because I imagine it's a very complex problem. So where do you start then?
So there was, of course, a number of fundamental technology challenges around this source, right? And one being from how do you generate most light, right? How do you crank up the intensity, which required certain changes in the light source architecture, in the lasers, in the laser concepts, but also how, for example, that laser in the end interacts with the tin droplets that actually generate this EUV light and then bring it into the scanner to be used for exposures.
Did we then already, have the let's say the source concept? Because there were actually various options to deliver the power. So was the decision already set then that it would be this laser-produced plasma where we would hit the tin droplets with a laser, or was that still?
By that time, I think we still had a number of them, right? So
correct.
That laser-based system that we always used, but then there was different concepts on how you would actually have that light interact with the tin, which then ultimately would irradiate that EUV light that we were after.
And would you also have to deliver that solution then, or was that research? Or
well, the research would normally do the pre-work in terms of they select the concepts, and then once this goes for productization, this would normally be brought into a program, which then there's a whole load of engineering required to bring that into a product that you in the end can ship to a customer.
Okay, and if you look then at the customers, what would you tell them? Because I imagine they would look for some commitment or promise or whatever. So in that early days, what did you guys tell the customers then?
Well, of course, it's first of all about show and demonstrate why EUV is a good thing. So talk about the value that it has to them, right? I think that was the first key thing. That they need to basically support the idea and see that in the long run it brings the value to them. But then, of course, along the way, when you're doing a few watts of power, you need to go to 250. Yeah. And of course, you're transparent on what you know. So you try to depict the plan that you have. But of course, along the way, we had many, many adjustments. Yeah. So some of the stuff that we are trying, it works or it doesn't. And I remember from all those conversations, you cannot say, well, it doesn't work and sorry. You always have to basically, what's next? Because I think everyone realized that the value was so big that they wanted us to succeed on this.
Yeah.
Which means that if you have a setback, and then of course also with the engineering team and the product teams, what's our next step? What's our plan B?
Yeah.
And that was a continuous effort. Talking to customers and basically making sure that also they kept on believing in what we were doing.
Yeah, I think in that context was also very important that there were two things continuously very important. One was the fundamentals. So could it work?
Yeah.
Could people see that it could work? So is that credible in itself, right? So there were a number of technology channels in that. And the other part I think which was very important, which we always focused on, you have to continue to show progress.
Yeah.
Right? You have to continue that you make progress, although that might be slower than what people expected or what you would have wished yourself.
So what was the initial, let's say, promise? What did we communicate to the world when we would have this 250 watts? So the expectation versus reality, we can say in hindsight. How many years did we sort of?
I think
extra?
Intel was kind enough to keep track of that. I think they had a nice slide where they basically showed our roadmap progressing over time. And I think the first date was early 2012ish, I would say almost, top of my head.
Something.
Where I think the first time we actually delivered 250 watts at a customer was early 2018.
So that's basically 6 years after expected.
At least. But I'll probably need to look up the details on the exact number. But it was significant.
So coming back to that customer trust, then what is then key to keep them on board, to not lose them with let's say promises or commitments that you cannot live up to?
I think it's two things: transparency on what you're doing, and earn the credibility to show that the steps that you're making, that you know what you're doing, that they see what you're doing, and it works. Of course, you will not make a big step at a time.
Yeah.
But I think all the small steps on top of each other keeps also them engaged on this.
Yeah. And what was the reason for the delay, Herman? Was it unexpected problems or known problems that took longer to engineer, or a combination?
No, I think most of the delay came from the fact that you're running into unexpected things. Because, of course, particularly on the EUV source, we were in unknown territory. I mean, we were literally doing things that have never done before.
Yeah.
And some of the things were actually foreseen, of course. So you kind of build in some mitigation in your design or deal with that in your plans. But there are also parts that we ran into new things that we were simply not aware of.
Yeah.
But which required then significant adjustment, either in the product, and as a result, you also need quite some time for that. Yeah. And that could be things that were setbacks on things you were already working on, but we also ran into new things. Right?
Yeah.
So with the source power going up, for example, we also ran into new problems in terms of how to manage this violent explosion of this tin droplet, and how to contain that in a way that you could actually keep on doing that over a prolonged period of time.
Yeah, so it was not simple engineering, whereas it required quite some inventions in many steps to get to the required power levels.
So you also took customer feedback and technical suggestions on board? And,
all
the time.
And you have to imagine that the pressure also on those customers was on, of course. I mean, particularly when they had systems already. I mean, they needed to start yielding some research results or technology development results. So they also sometimes started to think with us in terms of, well, maybe you should do this, maybe you should do that.
And they send over people?
Oh, yes.
Oh, yeah, also happened.
Send over people here, also San Diego, even to some of our suppliers where we had in-depth reviews on certain parts of the system, definitely, yes.
And in all those delays, did you ever think, this is never going to work, I'm going to give up, or...
I think fundamentally for me, no. But of course, you have your ups and your downs, right? So you also sometimes go home late in the evening, feel like, well, no clue how to do this. We have to start tomorrow morning, right?
Yeah,
but then I think it's also one of the nice things of ASML. You always end up then together finding a path forward, right? Finding a path forward. Or somebody comes to you and says, well, I have this one idea, right? Yes, so it has its ups and downs.
Exactly. So also after sometimes pretty bad customer meetings where you don't have a good story yet. It's like, okay, what do we do next? Because
so you always had some sort of idea.
I think if you look to the whole team, and of course that was a very big team, I don't think there was at some point we said, well, we don't know, we give up. I never felt that myself. It was always like, okay, we had this setback, but okay, get the right people in the room and let's see what we can do. I think there was always this mindset, okay, what's next? We're next. There was never something like, should we stop? I never had that discussion, never. No.
Well, more, I think in a broader perspective, of course, this was one of the big challenges. I mean, first of all, on the customer side, of course. So how do you maintain that trust and that credibility as you are delaying and not delivering? And so making progress was an important one. But at the same time, the same would happen in the supply chain, right? So you would have suppliers that went through a lot of effort to get something to you in time. Waiting for a ramp up, which was not, which was also shifting out.
Have the capacity ready, the volume?
Next year. And also there, the credibility also was an issue at some point.
So would you also talk to suppliers then, or did that go via sourcing?
Definitely. No. So we
not just the key suppliers, but
well, from my role, I had interact with some suppliers. Yes, of course, the ones on the laser, of course, the optics. Yeah. Also some of the mechanical parts, definitely. Yes.
Yeah. And how do you keep the team of 3,000-4,000 people then motivated? Would you celebrate small successes, or would you?
Definitely. I think as also there, also every month when we had our source reviews, I also give an update. Okay, what's happening with customers? Where are they? Are they committed now to EUV? What are their plans for EUV? How are they deploying it, etc.? So that's always, you also try to explain what's happening on the outside, which is also a motivation for inside, right? Yeah. As we see 3-4 customers are going, of course that also creates momentum. Yeah. I think it's difficult when only one customer was going, of course, but you have to show what's happening outside.
That's a very critical element. So particularly the internal teams, they like to understand what they're doing it for. So they like to see also what it means for customers. And they like to hear that. And it almost is. There's a lot of repetition in this, but it's very important to keep the end goal in mind. Because you're talking about a significant group of people that all working on a single goal, right? So and having that alignment and keeping that alignment and keeping everybody aligned and focused is one of the big challenges. Yeah. Right?
And I guess there's no golden recipe for that, right? It's
well, it's again one of the elements that Marco mentioned. There's also in transparency inside, right? So what's going well, what's not going well. Talk about setbacks, also how we will overcome them, but also have proper celebrations if we met certain milestones. But I think it's also about connecting. I think you did quite some work also bringing customers to suppliers.
Exactly.
So to be able to talk to each other.
Yeah, and also I think as a leadership team, you have to radiate that you believe in it, right? Yeah. If you don't believe in it, I think that will not happen. Then it will not happen. Yeah. So you have to, and it's also your internal credibility. If you have setbacks, talk about it. How are we going to do it? If you have successes, celebrate them. Yeah.
And what was your most difficult meeting, internally, externally?
Most difficult one. That's a good one.
It's probably.
Well, I think for myself, one of the most, in hindsight, the least nice, I would say, was some of our outlooks on our availability roadmap. Oh yeah, where we were pretty bullish in meeting what our customer would need and also what we agreed with them. But I think when we showed our plans, we really did not know what we didn't know. Yeah. So we were overly ambitious, and in hindsight, we had no clue what was still going to hit us. Yeah. So I think that was we were a bit opportunistic there. I would say that. But on the other hand, having that target also helped. Yeah. Big time internally.
You need to have a focus.
We need to have a focus. It wasn't say, okay, with 80% uptime we're good enough. No, you said, okay, we agreed to 93. It will be 93. Yeah.
So is that mindset then the most important factor to accomplish it in the end, or what? There's many things I can imagine.
It's one of the key ingredients. Yes, it's mindset. It's teamwork. Yeah. It's I think transparency. I think that's the key
honesty
word.
Is very important.
Honesty.
Right. So we talk about most difficult meetings. I think there have been quite a few, but I think one of the most difficult questions I ever had, which is almost an obvious question. So, Herman, why should we believe you this time? Right?
Oh yeah.
And what did you say then? Answer that. Oh yeah, you just start explaining what you're doing. right? Because in the end is you can say, well, because I'm there, right? But in the end is about the whole thing, how everything adds up, the different plans you have, the different technologies you have, the different parties you have working on the different topics.
And on the first steps that you're taking, are those pointing in the right direction?
Yeah.
And it's also about taking away roadblocks, right? I mean, we had this, of course, the source was the main focus, but at some point, when I think we got some visibility towards more source power, I think it was at 80 watts already, right? Customers also bringing up new problems. Saying, of course, we had this whole tin management issue. How do we keep the mirror that directs the EUV light? How do we keep that clean with all this amount of tin debris? But also the pellicle, you were still involved in that.
Yeah, exactly. Also there. So, okay, suppose now we have light. How do we keep our reticle clean? Because we cannot use a simple solution that DPV has. So also there, those questions came. How do we do that? How can we keep the system clean?
So one solution led to other problems, perhaps, or
other challenges again. So how do you do that? Suppose you have the light. Now then what?
Yeah.
How do you keep our mask clean? If you have the power, how do you get the uptime? Are the parts lasting?
Which was also a credibility issue in the end, right? Because for deep UV systems at the time, that question would not be on the table because you would have suppliers making pellicles, which is kind of a protective layer above your mask, right? And for EUV, it didn't exist because most materials would not be transparent to EUV light, so it kind of defeats the purpose. And then there was some materials, but these we're talking about thin layers of I think 30 or 40 nanometers.
Even less
thin. So it's you cannot imagine how thin that is, right? But you could not handle these things, right? Because you would touch them, you would break them. So just being able to handle those and having a mechanism how to do that didn't exist. And nobody was going after that because, well, then you had to invest money, which means you were believing in EUV to happen. And most people were just waiting.
So you have to develop all these new competencies along the process, or
you almost have to form the ecosystem, prime the ecosystem.
Especially on pellicle, indeed. There was we started ourselves indeed, and in the end found a supplier to work with, but it didn't exist.
So Herman, what were the key technology breakthroughs?
Well, in order for me to answer that question, I first have to explain a little bit what we were doing. So we would have a huge laser, and that laser would fire a laser beam on a small tin droplet in a vacuum chamber. The tin droplet would kind of explode and radiate light, EUV light, that we were then collecting with a big mirror and sending to where we wanted to use it. And the first technology breakthrough was actually that we introduced a pre-pulse on the laser. What that pre-pulse was doing was actually expanding that small tin target, that tin droplet, to a larger pancake. So it became easier to hit with the main pulse of the laser. I think that was the first one. And then later we found out once we got that, which was a complete new configuration, that if we do that some of that light on that tin target was actually going back reflected into the laser. And that meant that also some of that back reflection was actually taking away some of the power of that laser that we needed actually to hit the next droplet. For that, we developed an isolation module, which is kind of a light switch, but not for electricity, but for light. So this is pretty high tech. And once we got that, there was a third challenge because we were by then hitting that tin droplet so aggressively with so much violence and so much energy that this tin droplet was exploding, but the tin debris was going everywhere, including towards this mirror that we needed to direct that light into the scanner, into our system. And of course that we couldn't have because then the reflectivity of that mirror was going down, and as a result we would have less
So you
less
generate
power again.
more EUV, but it doesn't get into your scanner.
Okay, it's absorbed or...
But these were 3 big ones that we did. But they all took easily more than a year, sometimes multiple 2 years to develop.
Okay, and if you look at the power, not the roadmap, but how it actually grew, was that like a steady growth, or was it like a step function almost, like if you delivered something, or how? I mean, could you sort of show, okay, we're going in this direction and we'll get there, or?
I think there were a few steps being made also with the introduction of new source type, new products where we made steps, 40 watts, 80 watts, 125 watts, and then of course the jump to 250 watts. So I think that went stepwise because it was also linked to some of the big changes that we made in the system. So it was not a gradual percent a day. There were really some steps made, and those steps were big and difficult.
Yeah. Marco, so overcoming these technology issues, is that always a matter of pure hardcore engineering, or?
Well, take the example that Herman just mentioned, the fact that this collector mirror was contaminated. Of course, we try to approach it in a very systematic way, where we're looking at different flows around the collector, different geometries where we could influence the settlement of the tin. But none of that actually really had a big impact. But we did see that sometimes over the weekend, when we did maintenance to this chamber, this vessel, we actually saw that mirror's reflectivity was improving actually. And first we thought, well, this must be some artifact of a measurement. But it was consistently there every time we did some maintenance on that vessel. And this is where I think a bit of luck also came into play, because when we then on purpose said, okay, let's open it up and close it, we could reproduce this effect. And then with some smart chemistry people around us, they actually found out that a little bit of oxygen in that chamber gave a chemical reaction that was actually cleaning this mirror. So this was something that, although we were looking for a solution, we found something that we're not looking for actually.
Yeah, it was a lucky coincidence.
This was a bit of a lucky coincidence, yes. But nevertheless, it was also a big breakthrough in terms of how do we keep this collector mirror clean.
And when did you know we're going to get there? Now I know for sure.
I think it was 2016, right? End of 2016 when we saw the feasibility results of the 250 watts.
Yeah, exactly. I think at that time we had our first internal results on the so-called seed isolation module.
That was in San Diego.
That was in San Diego, yes. Where we did see, okay, this technology has now the potential to go to 250 watts.
Okay.
I think from there on it took till I think the day or the week before Christmas 2017 that we actually had the first proto system in San Diego showing the 250 watts.
Continuous.
Which was, continuous. That's for a couple of minutes at that point in time. So that's exactly. Continuous. And that was, I think, a big breakthrough for everyone. I think we're all in very close contact with customers. I think the stories have been shared before.
Yeah, that's true.
I think we were spread over the globe at customers.
I still remember that we showed the results and everybody was enthusiastic and very very anxious still and a lot of anxiety to get these also for people to also get it in their fab.
Yeah, right.
But then we also showed the setup with which it was made, and that was clear that it required significant work still.
Yeah. Do you still remember where you were when you heard it? Was it behind your desk or?
No, I was at a customer somewhere in Asia.
And then you got a message, or?
No, we actually were preparing for an executive meeting the day after, where having this result was a key ingredient.
And it came. Okay. And you were there as well at that meeting?
I was not there. I was not there at that customer. I was here.
Yeah.
One of the buildings over here. Still remember that we saw the email also coming in, right?
Yeah.
First pictures, and then you're like, you're gonna sit back for a moment. It's like, we have it, right? We have it.
Yeah.
But it was also a moment where I saw the customer was relieved.
Oh yeah.
Okay, so it was
many people.
Many people were relieved at that point.
But then the big work started, of course, because then this whole lab setup needed to become something that you could ship to customers.
Yeah.
So the pressure is only higher because now customers have seen it. Now they say, well, why you take 18 months? Why you cannot do it in 12 months? Why
exactly.
Right?
And if I want it in my fab, it's just a day of upgrade, right? Maybe 3 days, but that's it, right?
Yeah.
Well, I think in hindsight, it was 4 weeks.
Yeah. What do you think the secret of ASML is? If there is a secret, what is... Another way to look at it is, why are we now where we are?
It's not a secret anymore if you tell them.
It's a secret. We cannot tell it,
okay.
Mark.
Well, next question.
I think one of the...
No, I think that it's about key strengths. I think it's... I think in this one in particular, I think a strategic direction was set. And I think the fundamentals that were very strong. I think everyone was convinced that if you pull it off, there's a huge value in it. So that's a key thing. That's where it starts. Having a great vision and a great goal. And then, of course, having a whole team that has a mindset to make it successful.
Teamwork.
Yeah, team.
And the teamwork not defined as the team within ASML, but the team with the customer, with the supplier. The whole chain needs to cooperate to make it happen.
Yeah.
Right.
Okay.
And I think that was.
I think that was key. I think even if you talk to customers today, sometimes you look back to what happened and they still said, "Well, that was an interesting period this year."
Yeah.
Oh yeah, they all know.
They all know. They
all remember.
And with success also comes the danger, if you will. If you are the incumbent, so what is the danger to ASML? You think now? Where should we be aware of?
I think it's twofold. I think the obvious is complacency, because we are where we are. we did it, and as such we can do we can get away with everything. I think that's a very, very big risk for us.
Yeah,
we should take nothing for granted. We're not entitled to anything. And the second is also because we did this one, we pulled this one off. We think we can do everything.
Yeah,
which is also not always the case.
Yeah.
So I think also there we need to be a bit modest and humble.
Yeah.
To take on all the challenge that we want to take on.
Yeah.
But that's...
I think that, as part of that, just adding to that, I think staying close to our customers. Because we got the amount of direction we got, also the amount of discussions we had, the interactions, based on where they also mentally were in terms of what they expected from us. I think that was also proven critical.
Yeah.
To be able to keep everybody on board.
Yeah.
And it should be, I think, a key ingredient of all our big developments moving forward.
Yeah.
So how do we keep that spirit then?
You have to make sure that one of our key stakeholders are our customers. So we have to always understand, what do we do for them? What do they need? How do we can add value?
Yeah.
And it has always to be a central question in our developments. And if we cannot answer that question, then we missed a few discussions with our customers and we need to go back.
Okay.
And it also means hard work. I mean, right? It means that you have to really spend time bringing this customer interest, customer voice into the organization. Right?
Yeah.
Whereas maybe 10 years ago we were somewhat smaller, this was what easier. But now this requires significant focus and work to make sure that happens.
Okay. And the last question, what are you most proud of?
To me, I think it's almost the same thing as what's the secret, because I think the teamwork I think was incredible. I mean, to be part of something like that is just, it's difficult to describe even. I mean, the pride that people feel, the sense of belonging, the sense of achievement together, right? Because it's a lot of work. It's a long period, right? 10 years.
Yeah. The commitment from people, the dedication to them. I think we had people in every day of the week,
nights. It didn't stop.
It didn't stop. No.
Yeah. So, and I think that happened in our place. It happened also at our suppliers. It also happened at our customers. It happened all over. And I mean, and to be part of that and have the privilege to be part of it, but also have a leading role in that. Yeah, it's like living a dream.
Yes, definitely.
Okay. Same for you?
Maybe to add to that, I think when our goal was, let's say, the 250 watt, 125 wafers per hour, and once achieved, actually a whole roadmap we developed with systems on top of that. I think when at least when I joined EUV, I think there was a 3400 system, which will do the 125 wafers per hour, and then there was high NA, and there was nothing in between.
Okay.
And I think once we had, let's say, the success of that 3400, then also new systems were defined and actually it developed to the whole roadmap, which we're still executing on today.
Yeah.
Another great work started.
Okay. Yeah. Well, guys, thanks a lot. I really appreciate you being here, making the time available. It was very insightful. Hello, Arie. Welcome to our podcast.
Hi, Mark.
Can you give a quick introduction of yourself?
Yeah, so I'm Arie Boef. I've been at ASML now for 26 years, more than 26 years. Before that, I worked at Philips for a long time, many years, always working in the area of optics, but my background in studies is electrical engineering. Mm-hmm. And at ASML, I've always enjoyed working in the area of optical measurement systems, so the alignment sensor that measures the position of a wafer, level sensor to measure the height of a wafer. And this last years spending a lot of time on exploring new optical techniques to really characterize the structures, the patterns that are on a wafer.
And you're a fellow, corporate fellow even, right?
That's right, yeah.
What is a fellow and how do I become one?
Well, generally a fellow is somebody from, let's say, from the technical community, so an engineer who generally made a substantial contribution to some of ASML's products. So something that has made an impact on ASML's product portfolio. For example, talking about myself, it will be, let's say, the YieldStar sensor, where I had the pleasure to be part of the team that started YieldStar.
We want to talk about that journey. So when did you first get the idea for such a machine?
Yeah, that's a very nice question, because I always liked that part of the story. Is I got interested by it because of my background when I worked on the alignment sensor. A bit of technical background. In alignment, you measure the position of a wafer, and you do that by measuring with an optical sensor on grating, so periodic structures present on the wafer.
Yeah.
But if those gratings get deformed by the wafer processing, that alignment sensor starts making mistakes. One way to measure or to minimize those mistakes is if you know the shape of that grating structure, you are theoretically capable of correcting for those errors. In those early days of me at ASML, when I worked on alignment, I got very intrigued and fascinated by the challenge. How do you fix that resulting measurement error from an asymmetric grating? And then I thought, well, if I could somehow reconstruct the shape of that grating just from the light that is scattered by the grating. And I read a bit about what is already done in literature. I basically had a lot of conversation with people around me, and then I just got this idea, well, what if I shine light on a structure, on that grating, measure the backscattered light, and just give it a try. See if I fail or succeed. I didn't care in those days. I thought, let's just give it a try.
Yeah. And could you just build a contraption then to measure that? Or?
Not immediately. In that period, I was still working in the D&E department, so development and engineering, where I had my other tasks to complete. So I worked on it kind of on paper, just paper study in a rather below the radar screen activity. But my department manager in those days, Jan Willem Martens, he was aware of it and he supported me in that. But it all changed at some moment when suddenly Martin van der Brink started asking questions around by mail, like why is nobody looking into that technique called OCD, scatterometry, where you basically do exactly the same as what I was trying to do.
Yeah.
So then, based on the mail from Martin, Jos Benschop said to me, well, why don't you come to research, the department that Jos was heading, and what you do below the radar screen in D&E, you can certainly do it above the radar screen in a more official capacity.
Yeah.
So I moved to research.
Yeah.
Initially first worked on it on paper. We started a collaboration with Philips Research, where I also have my roots originally. I knew quite some people there. And then slowly I got this idea in my mind how it could be done in a somewhat different way as what our competition was doing. But in those days at ASML, we had no infrastructure to really do experiments in a research-like manner. So I went to Jos and asked Jos, well, Jos, are you okay that I spent a few months at Philips Research, where I had my friends, my network? And Jos said in a very practical way, okay, just go and arrange it, do it. Yeah. So I spent 3 months, or 4 months actually, at Philips Research with a former Philips colleague of mine, Jan van der Werf. And I had the opportunity to build something from essentially very old material that they didn't use at Philips Research. Built the first breadboard.
Yeah.
I still have the picture as a sweet old memory.
Yeah.
From that first breadboard, I did some measurements. A few months later, Jos and I went to Martin, showed us first measurements. Martin got interested.
Yeah.
But of course, asking critical questions like, why would this be better than competition?
Yeah.
But in the end, he liked it, and he basically told me, make me a real research proto out of your breadboard.
Yeah.
Come back to me in 2 months' time with real data from that prototype.
Yeah.
Now, that was sort of mission impossible.
Yeah.
Because ordering stages took already 8 weeks to have them delivered.
Yeah. Yeah.
Now, you can argue 8 weeks is less than 2 months, so why complain? But all the software had to be written, the sensor optics had to be designed. So Jos helped by assembling a small team of people to really help with this new endeavor.
Yeah.
And with a group of about 12 people, and by just bypassing all the official rules of developing a product here, we managed to build that prototype in 9 months' time.
9 months.
So we overran by a factor 4.5.
Yeah.
But at the end of the day, Martin was happy. He was pleased.
It worked.
It worked sufficiently well to convince one major customer that this was something worthwhile following up. And after only a meeting of maybe 1 hour, IBM was essentially convinced. They said, well, this is sort of what we were hoping to get.
Yeah.
And please, can we have a real prototype of this tool?
Oh, wow.
And I was quite excited about it.
So then you had to build a real tool.
Yeah. So then we built a real tool. And then, of course, we had to scale up. Then it is no longer a research-only activity.
Yeah.
So then a real development team was formed. Stefan Keij became the PDM of this activity. And it means you have to talk with a lot of other companies.
Yeah.
Like you need stages, you need a track interface.
Yeah.
You need software.
Yeah.
We had to start from scratch.
Yeah. And when did you ship the very first machine? Do you
The very
remember?
first machine was, I think, shipped. That must have been around 2006 in that period.
Yeah.
And it was indeed, as expected, shipped to IBM as the first customer.
Yeah.
Their application space was really, let's say, litho control. We learned the hard way that the application space that we initially had in mind, CD control or CD metrology and control, just was a heck more difficult than what we had ever envisioned.
Yeah.
And we also started talking with another major customer, being TSMC in Taiwan.
Yeah.
And they ultimately, they were our big saviors, because there we had our number one champion, Dr. Ke. He liked the whole concept of YieldStar a lot, but it was the overlay metrology capability that he got excited about.
Yeah.
And which, by the way, when I started working on it, I always thought that CD metrology was the big opportunity.
Yeah.
And overlay was just a nice thing to have.
Yeah.
But after all these engagements with TSMC, I learned that I was completely wrong in the end.
Yeah.
That it was actually the overlay metrology that was the big opportunity for the YieldStar.
Yeah.
While for CD, we had to come to the conclusion that for CD, our customers had other alternatives that were already established there.
So now it's been a success, right? Because next month, April, I think we're going to ship the 1000th machine tool, right?
Yeah.
How does that feel for you?
Yeah, I feel very happy and glad that I had a chance to be part of the team that had the chance to kickstart this activity.
Yeah, yeah.
The only regret that I have, looking back, is that I did not take more pictures in those early days.
Okay.
In a sense, I have almost no souvenirs left from those days, because in those days, I started it as a researcher that was excited about trying your own ideas. But I never could have envisioned that it could grow into something to where we are today.
But did you always believe in it? Like were you convinced it would be a success, or was it more like, hey?
Well, to be honest, the honest answer is no, because I still remember the first PowerPoint presentation, and that I still have, by the way.
Okay.
That was a presentation that I kind of presented in a research review, where I presented to the stakeholders the status of this work. And I still remember the closing slides of my slide deck. That was end of 2003. When the concluding remark, I said, well, the first steps have been quite promising. The first results show potential. But then my last remark kind of showed it all. I said, I want to continue working on it until I find a showstopper why it cannot work. And I can now say,
very academic statement.
It's kind of academic, but 20 years later, it's still alive and kicking.
You still haven't found the showstopper.
No.
So what did it? Is there a lesson to derive from this?
Well, what drove me is a certain belief in something that I wanted to prove to the world. Because I always had that feeling that if we can, with light, reconstruct the shape of a grating or analyze the grating, I always believed there has to be value in it for ASML.
Yeah.
In those days, I could not quantify it. I had no story behind it.
Yeah.
Martin always challenged me on that. Like, why is this good?
Yeah.
And by the way, he never got a good answer for me. And he still reminds me of that day.
Yeah.
But I always had that passion or energy to really, this belief, I'm going to show it, no matter what it takes. And
Is it also trusting your instinct, your gut feeling?
It was all driven by instinct, If I could in no way prove it, it was my instinct that somehow we as ASML have to look into this.
And what is your instinct telling you now? What are you now? What is the next brilliant idea?
That's a good question because what after all these years, so a few years ago, ASML offered me the opportunity to spend 1 day per week in an academic environment in Amsterdam. And in such an environment, you have the freedom to look in something completely new again. And what several years ago, what I see as a trend that to keep on improving YieldStar, there are plenty of ideas to improve it, but it all boils down, you make the optics better, you make mechanics better, you basically make the hardware better. It can all be done, but the general trend is it makes everything more and more expensive. If you want to improve the optics, you need to improve the polishing of the optical elements, better coatings, better everything. And that rapidly drives up cost. Now, today, cost is a big thing in litho, especially metrology. So there is a huge drive to reduce cost while keeping the performance at the same level. When I got the chance to work in academia, so at university for 1 day per week, I thought, maybe a nice research question from an academic perspective is to think about, can you somehow simplify the optics in YieldStar significantly? Meaning you get a simpler sensor, hopefully with lower cost, but then you get a degradation in the image quality that you measure. Then the idea is, can you somehow use smart algorithms to basically restore the image quality to what it should have been if you had used good optics hardware?
Okay.
Now, when I first shared that idea with Christophe Fouquet, who was in those days business line manager of the application BL, his first response, I still find it the most inspiring feedback that I ever got from somebody. His first response was, I don't believe that this can work, but if it works, I want to have it right away. Because that short feedback contains everything that you like to hear as a researcher. Because it basically shows you that the idea that you have is crazy enough that people don't believe you. But they also say, if it works, please give it to me.
Okay.
Again, what helps here, we have a team of very talented people here at ASML, but also in Amsterdam, who are also deeply involved. And what I really like about this, and that gives me a lot of energy to see that an academic team in Amsterdam is very well connected to the industrial team in ASML. They really work as one team, one goal, but of course in a different way. The academic team has this academic freedom to explore, let's say, the more far out options. But they are so well connected to the ASML team, who is working on more tighter milestones. It's great. I like what I like about to see how much energy my Amsterdam colleagues get from the industrial interest. And what I like to see is that my ASML colleagues spontaneously reach out to the academic world to basically consult, hey, how could we solve this, for example? And I find it it has always been my dream to work in such an environment.
And do you want to place a bet? Will it be a product?
Again, quoting what I mentioned earlier on the earliest YieldStar, I have not yet seen the showstopper. What I have seen is tons of challenges that still need to be solved.
Yeah.
But of all these challenges, at least we have ideas how we think we can tackle it.
Yeah.
And it all remains to be proven if it works to a level that is good enough.
Yeah.
So I'm
still optimistic.
I'm optimistic, but I can't promise it, of course. Yeah.
Well, then we'll invite you back next year or so. But
I look forward to that.
For now, I want to thank you for this inspiring story. It's research is perhaps an area that we don't see all the time, with all the machines and products and customers. But I think this has been very insightful. Thanks for that. And
thank you. It was a pleasure being
here.
With
your endeavor.
Thank you. Thanks, Mark.
Hello, Dan. Welcome to our 40-year podcast. You're joining us from the US. Could you give a quick introduction of who you are and what you do?
Okay. Well, first, let me congratulate everybody at ASML for 40 years of excellence in lithography. That's quite a feat. And as far as who I am, I've been in the industry since 1978. And actually, I grew up in it because my dad was a solid-state physicist, which really got me the leg up to meet all these people. My background's economics, but and I kind of plowed this untouched ground in the industry for really figuring out how to forecast it, how the economics of the industry worked, all the different layers to it, that sort of thing.
Okay. So we could describe you as a hardcore industry insider, right? And how would you describe the semiconductor industry to an outsider?
So, and then how do you describe the industry? Well, everybody's seen pictures of President Biden or, the various EU government officials, Japanese government officials hold up semiconductor chip and say, these chips are in everything. And anything that you see as smart, it's only smart because there's a semiconductor inside of it. It takes a chip to bring the intelligence to it. And but what ASML does is a layer down from that. And it's kind of interesting because the chip is based upon, you make them on a wafer, you make hundreds or thousands of them on a single wafer, and they're this layer like a club sandwich with all these different layers that you put down in pattern, and and in a sense they're essentially generic, except for there's a chip designer that puts patterns on the chip that actually make the chip do the logic that you want. But to make the wafer, that's what ASML does, and that's the equipment that goes into it. And in fact, you wouldn't have a smartphone if it wasn't the equipment, and you wouldn't have an iPhone if it wasn't for ASML. And and so these are sort of the things that the industry works. But the equipment companies tend to stand in the background while the chip companies get all the glory.
So I guess the driver that we want to zoom into today, the driver for the chip industry, a big one was the introduction of the iPhone. When was it? In 2007, I think, when Steve Jobs announced it.
Yeah.
Can you still remember that? And did you immediately recognize it as a big booster or driver for the industry?
Well, most people didn't recognize it. In fact, many of the pundits that were following the smartphone market said no one's going to buy this phone because it doesn't have any buttons. In fact, BlackBerry made exactly that mistake.
Yeah.
And I remember thinking, anything that Steve Jobs created, you should pay attention to. So the first day I went to, I avoided the Apple store in Palo Alto because there was a line around the block. And so I came back on Wednesday afternoon, walked in, started playing with it. And I said, wow, this is kind of different. So I bought one to see what it was. I knew very quickly that it was going to displace Nokia, the world's leader in the phone market at the time.
Yeah.
And it would displace BlackBerry as well, and Palm, who were leading the smartphone market. But that kind of gets the cart before the horse, because the iPhone would not have been possible had the Moore's law continued to improve power and performance, and that would have not been possible had ASML done the 193 and then kind of rescued the industry with 193 immersion, which was coming at the time.
Yeah.
Because it's the tools that actually bring the electrical performance to the chip. Otherwise, the iPhone probably would have run out of batteries every 30 minutes, and no one's going to, at the time, a phone cost about $100, and the iPhone was $500, and who's going to buy a $500 phone that lasts 30 minutes?
Yeah. So actually, let's say that the power consumption that was enabled by lithography immersion, you think that's the big, let's say, differentiator or driver? Would that be fair to say then?
It is the driver. I mean, so you have two things. You have a supply side and you have a demand side. The demand side is people wanted to be able to access the internet. They wanted to have their music on their phone instead of carrying a pod. That was Steve Jobs' presentation. If you go on to YouTube and look at his presentation, he's talking to the demand side. The supply side was that phone would not have been possible had the things like the flash memory had evolved, the CPU had gotten to the point where it didn't consume all the power in the phone. You could actually run the screen because the screen was a big power hog back then.
Yeah.
So those are the sort of things. And then that meant you needed to make the transistor smaller. You needed to reduce the leakage in the transistors, which could only be made possible with equipment. And it wasn't just ASML, it was Tokyo Electron, Lam, Applied Materials that were also providing the deposition and etch equipment that allow you to actually pattern those layers. But at the end of the day, you can't get the resolution without the lithography tool.
Yeah.
And that's where ASML came in.
Yeah. So where do you think the big drivers for the industry will be for the next 5 years?
Oh, I definitely think it's going to be AI. Smartphones have matured. Smartphones are having their PC moment. So, we had the PC matured and it was they'll still grow like the PC did in the 2010s, but they won't be growing at, massively high growth rates because virtually everyone has one now. And so the driver for the growth is just not there, where AI is coming in. And AI is really a different animal than the smartphone because it's more a fundamental technology as opposed to something you're going to go buy. You will buy AI through using the app.
Yeah.
But the AI is going to be very data center centric, which, when the iPhone was introduced, the internet was in its infancy and data centers really weren't that relevant yet. They were just becoming relevant.
Yeah. So AI in that sense is more like a sort of a container that can fuel all kinds of applications that you can work with, right? So
right, like ChatGPT. I go on my PC or on my phone, I ask it to give me some text, and it gives me some text.
Yeah.
A designer wants to design a chip.
Yeah.
Today, what they do is they go in and they literally use AI to create most of the code today, so that it makes them more efficient at designing chips.
And if you look at us as equipment makers, is it then what we will feel? Is it the sheer volume of chips that is needed, or is it also a shrink drive, or is it another thing? So how will we as equipment makers, how will we sense the need for AI and AI chips?
Well, if you look, the world is moving from traditional computing to accelerated computing. And with traditional computing and a CPU, because everything is serialized, the actual number of transistors that you need peaked. And so the chips have gotten smaller, but you haven't needed more transistor. Where AI always needs more transistors. It can always use more transistors because it's accelerated computing. You add more and more core to it. And so you need more core, and you need to pack them into the field size of the litho tool.
Yeah.
So that's the real interesting constraint, is the field size of the litho tool has become one of the biggest constraints as to what you can do.
Yeah.
And so you've got this whole industry that keeps pushing for finer and finer resolution. In fact, even though the cost per transistor is in logic is bottomed, people are still buying them because they bring so many new features. So we're shifting from a cost model described in Moore's law to a value-added model.
Yeah.
And that's becoming more and more important, especially in data centers.
Yeah. So it's sort of redefining the definition of Moore's law then into value. Is that what you're saying?
Yes.
Yeah. Okay.
Exactly. So we're moving from cost to value.
Yeah.
And for example, the difference is it costs you so much to buy a chip, but if you're running a data center and if the chip you buy saves you on electrical power because it runs more efficiently, that payback is paying back over many years.
Yeah.
So, and it turns out that the payback of a shrink today in a data center chip pays back itself in less than a year. The entire price of the chip you paid. So if you talk to the data center people, that's what they're beginning to look at as a value model, not a cost model.
Yeah.
Of course, they still want it cheaper, but the real decision point of whether they buy it or not comes on the value that we bring to the market.
Yeah. So how far do you think Moore's law can, in that value sense, still continue then? Is that decades or another 100 years, I would assume?
Well, we know we can at least skew 3 more nodes in shrinking based upon everything we've seen. Now we're bringing in chiplets. We're bringing in, we're integrating into the package. You've also got quantum computing, which quantum computing is Moore's law on steroids. Because now because Moore's law comes down to Kumi's law, which is about, computations per watt with, once you move to quantum. And then, of course, photonics is the other big thing because photonics have sort of gone from moving information from very long distances, from thousands of miles to it's actually going into the data center, connecting all the servers, and now it's beginning to get within the server itself. And the reason why is light's very power efficient in terms of communication. So.
Yeah. I'd like to go back to you as an expert, as a insider, outsider, no matter how you want to look at it. A question we've been asked a lot ourselves is, what is the secret of ASML or the secret of the success? And what is your idea? What brought us where we are today?
One is the people, but I think to me, the secret of ASML has been that it's Dutch.
Oh,
and I started my career, and we were in the middle of this huge trade war with Japan. And the thing that I learned when I would go to Japan was the Japanese say yes when they mean no. And the thing I learned when I started going to the Netherlands was they say no when they mean yes. That the first thing, they often tell you no because they don't want to disappoint you. And then they, both sides. I mean, the Japanese tell you yes because they don't want to disappoint you. But then you're disappointed when they can't do it. The Dutch tell you no, and then they do go behind the scenes and do everything they can to make it happen and then come back and surprise you with a positive surprise.
Yeah.
So and that's kind of been, really the history of ASML. And I have to say that to a great extent, working with Martin and Peter over the last 20, 30 years or so, they kind of exemplify that, that whole challenge the customer, find out what the customer really needs, not what they tell you they want, And so the Japanese were going by a model of listening to the customer, where ASML was trying to watch the customer and realize what was really important to the customer that they would pay for. And the result of it was ASML used its resources, its R&D resources, far more efficiently, and they didn't spread themselves out across multiple technologies. And so that's why I come back. It's a really important way of thinking. In fact, maybe someday someone will write a management book about Dutch style management, which, I have to say I learned from the guys at Philips. They taught me about it. And the Dutch management is really different from American management or Japanese management. And I have to say that that's really the secret that I've seen in ASML. And the hard part for ASML is how do they propagate that out now that they're such a global company?
Yeah.
And the thing of it is the people at ASML always ask the right questions. That's always been my experience, and that helps. And,
Okay. So with success come dangers, right? And in that sense, what do you think is the biggest threat or the biggest danger for ASML at this moment?
The biggest danger is complacency. Every lithography supplier that became number one has disappeared because they became too complacent. They began to think that just because they were number one in lithography, they were the smartest people in the world. They knew everything, and they stopped listening to customers. They stopped watching customers and just started throwing things at customers.
Yeah. So your advice would be to stay humble and keep that original spirit, right?
Yep.
Yeah. Okay.
Yep. Because just remember, when you're not working on it, there's someone out there trying to beat you.
Okay. Well, I think that's a good lesson. Yeah.
And it's the paranoid company. And just because you're paranoid doesn't mean someone isn't out there to get you.
That's true. Only the paranoid survive, right?
Yep. Exactly.
Yeah. Okay. Well, this has been very insightful, Dan. We would like to thank you very much for making the time available and to share your views on the industry and on ASML. Thanks for watching. Like and subscribe to stay up to date with everything ASML.